So recapping from last lecture, we discussed a way to find the inverse of a matrix, right? And I didn't give it a formal title to it, but in your book, they call it the inversion algorithm. So we talked about a method for finding the inverse of a matrix. Right? And so the idea is that we take a matrix A, we augment it with the identity, we perform Gauss-Jordan elimination, and of course we have the assumption, we assume that A is invertible, meaning that A inverse exists, right? So if A is invertible, we have an invertible square matrix, and it exists, the inverse of it exists. That means that if I were to apply Gauss-Jordan elimination, which means I'm going to make A into its row-reduced echelon form, it would become the identity, right? That only occurs if your matrix is invertible. And in doing so, in applying the elementary row operations upon A, you will also be affecting the rows of the identity matrix on the right. And when I do that, the identity transforms itself to the inverse. And the idea along with this is that the inverse A is a product of elementary matrices that are associated with elementary row operations. So that's the idea. The idea is that the product of elementary matrices when applied to A yields the row reduced echelon form of A, which is the identity. So that's what these E1, E2, all the way to EK elementary matrices represent. Each of them represent a certain elementary row operation that when I apply it to A, results in the identity. And in doing so, this very product of elementary matrices is in fact the inverse of A, because you can consider this as being multiplied, as if I were multiplying this to the identity. So when I apply these operations upon A, I get the identity. And when I apply these operations upon the identity, I get the inverse. So that's the idea, right? That's the big idea. So we discussed the inversion algorithm. Any questions about the inversion algorithm? Does everybody understand the procedure and how it's done? Your homework, the first part of your homework deals with finding the inverse of a matrix. Mostly they are 3x3 matrices. So is everybody good with this? Yes, thank you, Sam. Thanks. Okay, so we're good with that. And then the next thing we also discussed was the consistency, right? We talked about the consistency of linear systems. So we discussed how or when a system is consistent or not. and what conditions the vector that we're what conditions do the b values that we have to be in order for the system to be consistent. So we have two varieties, right? One kind is when the coefficient matrix is invertible versus when the coefficient matrix is not invertible. So when the coefficient matrix is invertible, what happens is we have a relationship with the values that we have for the b values, right? Where there is no restriction. There is no restriction or condition for the b sub I entries. And that's because if the coefficient matrix is invertible, then the inverse exists. And so related to this, there's this idea, right, that if A is invertible and we have a matrix equation, AX is equal to B, then this system is consistent. And does anybody remember what the word consistent means in terms of a system? What does it mean to have a consistent system?
That it has at least one solution, is that right?
Right. That's right. So it has at least one solution. So it has at least one solution. But if the matrix that we're dealing with is invertible, then not only does it have just at least one solution, it has only one solution. So it's much more specific. It's consistent and only has one solution. So let me write this a little bit neater. It has only one solution. And again, we don't necessarily just use the word only one. We like using the word unique. So let me write this as a unique solution. And what's that unique solution? Namely, my unique solution is the inverse of A left multiplied by the matrix or that column vector B. Because that's the case, there is no restriction for the BI, right? When I'm talking about the BI, I'm talking about the entries along the vector B. But what happens when the coefficient matrix is not invertible? Then what do we have? Then we have at least, right, the row reduced echelon form of A has at least one row of zeros, which produces a condition, right? It produces a condition among the entries of B. And we saw that in the previous in the last example that we discussed last class. So we have an invertible matrix. So when that's the case, so if that condition holds to be true, right? Then, so if a matrix is not invertible, if A is not invertible, and the matrix equation is still consistent, is a consistent system, then there are infinitely many solutions. Okay, so we have consistent systems, inconsistent systems. So maybe I should write that as two circles. We have inconsistent systems. All right, you know what? Let me do this like this. So this will be the set of all linear systems, right? All linear systems. So make believe this whole rectangle represents every system that ever existed, and they're all of them. And so of course we have two cases. Either it's consistent or it's not, right? So either we have an inconsistent system, or we have consistent systems, right? Yeah, pardon me. So either we have inconsistent or consistent systems, right? Either we have, that means inconsistent means no solution. So there's a whole bunch of systems that have no solutions to them. They're called inconsistent. And there's a whole bunch of systems that also, so they're either categorized in two varieties, right? Inconsistent or consistent. The consistent kind, there's two variations of that type of system. So you have a breaking of that. Which means that I have either one solution or infinitely many. Okay, so either we have inconsistent or consistent. Within the inconsistent systems, all of them have no solution. Within the consistent systems, either you have one solution to that system or you have infinitely many solutions. And so in a sense, all linear systems are categorized in three kinds. You either have a system that has no solution, you have a system that has one solution, or you have a system that has infinitely many solutions. And there's no anything in between. There is no system that only has exactly two solutions. There is no system that has exactly only 10 solutions, for example. You either have 0, you have 1, or you have infinitely many, and there's nothing else. So that's this idea. Okay. So we discussed that last time. So we talked about the inversion algorithm, we talked about the consistency of linear systems, and we'll continue on with the next kind. So we talked about these systems and they're associated with matrices, right? So I want to discuss a bit more about the different kinds of matrices. So far, what do we have?
We have linear and non-linear.
We have what?
Linear and non-linear matrices.
I think you meant to say another word, not linear.
Oh, I'm sorry, singular and non.
Right,
All these
right.
words.
Right. We have the following matrices. So again, it's just to we have non-singular, right? And singular matrices. Now, what's another word for non-singular?
Invertible.
Invertible. So non-singular means you're invertible. And what does singular mean?
Non-invertible.
Non-invertible. So we've been in this realm a lot. In particular, we've been dealing with these matrices, right? We've been exclusively talking about matrices whose inverse exists, right? A inverse exists. So these matrices are very, very special. They're the ones that we care about a lot. Non-invertible matrices means that the inverse does not exist. So for these matrices, when you try to find them using the inversion algorithm, something breaks down and you can't continue, right? You don't get the identity on one side, on the left side. But here you do when you apply the inversion algorithm. Okay. So remember we talked about equivalent. So let's stay here a bit. And we talked about equivalent statements. About non-singular, aka invertible matrices. And remember, this is where we listed out the different things that were the same. So if I were to say, the first thing is that A is an invertible matrix. Which means that A inverse exists. And to talk about inverses and invertible matrices, we also assume that, well, I guess we could have prefaced this by, I'm going to call this, I'm going to call this 2, okay? Call this 1. We have what are called square and non-square matrices, right? So what are square matrices and what are non-square matrices?
Square being n by n and non-square is anything else.
Right. So square means you have the same number of rows with the same number of columns, and non-square is when you have a different dimension of the number of rows versus the number of columns. So invertibility is exclusively for square matrices. You can't talk about invertibility with non-square matrices due to the fact that the dimensions don't always are going to match up when you switch around the matrices, right? So invertibility, we're dealing with square matrices. So A, we assume it to be invertible, which we assume it to be square, and the inverse exists. So does anybody know another statement associated with invertibility? So if you have an invertible matrix, what else is true? The inverse exists. That's what it means to be invertible. But what else is true?
But you just
So
said
some-
the equivalent statement, so like not what is it, non-singular?
Right. Non-singular is just like a semantic, like it's a synonym, right? So non-singular is invertible.
Right.
But we want, like, what else can we say about matrices that are invertible? It has a solution, but what kind of solution? And to what kind of system? It has a unique solution, right? Okay, so first we have to identify what kind of system are we dealing with. So if A is invertible, right, that means that the inverse exists. That means that if I have the homogeneous, again, this is a homogeneous system. Okay, this is a system where we have those, every linear equation is equal to 0. And so when we create the matrix equation, we have this kind of algebraic expression. So in a homogeneous system, what happens? There is only one solution. There is a unique solution, but what else is it?
It's also a consistent system.
It's a consistent system. Yes, it is. When we talk about invertible matrices, we're dealing with consistent systems only. It's always going to, the solution will always exist because the inverse exists. But when we have this homogeneous system and we have an invertible matrix, what would be the unique solution? Hmm? Anybody? It is the what?
The in the I forgot the word. I gotta look it up.
So look at this, right? AX equals 0. I want to find X. That's the goal usually, right? I want to find X. So what do I have to do? I have to get rid of that A next to it. How do I get rid of that A next to it?
A inverse.
A inverse. It exists, doesn't it? So that means I can multiply both sides by that. If I do that, then what happens? What happens on the left side of the equation?
A turns into the in the term. Yeah.
It becomes the identity. So I get the identity times the vector equals A inverse times the vector 0. But identity times X is what?
X.
It's just X, correct? That's what the identity does. It's like multiplying by 1. But then what is 0? What's going to happen when you have an inverse of a matrix, right? What you have entries in the matrix and you have a vector that has a whole bunch of zeros.
This
What
is
happens when you
the
multiply?
solution, right? I'm sorry.
What did you say? I think Sam, right?
Yeah, this is the trivial solution, right?
Correct. Correct. So when you have a homogeneous system and the homogeneous system has a coefficient matrix that is invertible, there is a unique solution, and that unique solution is called the trivial solution. And what is the trivial solution? It's this. It's the vector, the n×1 vector that has zeros in every entry. It's the 0 vector. The 0 vector is known as the trivial solution in a homogeneous system. Now, we discussed this, but I just want to hear from you guys now what you guys remember or gather. These statements should become part of your memory. When you talk about invertible matrices, there's a slew of things that we can discuss. Invertibility means the inverse exists. If the inverse exists, if I were to have a homogeneous system with an invertible matrix associated with it, then the trivial solution exists always, but it's the only one that exists. That's the idea. It's the only one that exists. Okay, what's another statement that's associated with invertible matrices? So the invertible matrix has a homogeneous system. In a homogeneous system has a trivial solution. What else? Every invertible matrix also has what? When you talk about the row reduced echelon form. So if you have an invertible matrix, every invertible matrix, what is their row reduced echelon form?
Identity.
Right. So for every invertible matrix, if you were to find the row reduced echelon form, you get the identity. And that's always true for invertible matrices. What else do we know about invertible matrices? And someone discussed this already about consistent systems, right? So if you have a non-homogeneous, and when I say non-homogeneous, now instead of having the 0 vector, I have another vector where the entries in B are not all non-zero. So when I say non-homogeneous, homogeneous system means that B does not has at least one non-zero entry. So if I have an invertible matrix A and I have a non-homogeneous system, then what? Then the system is consistent. And not only is it consistent, it also has a unique, again, solution. But what's the unique solution? And we already discussed this, but what is the unique solution? How would you express the unique solution? We talked about it, like right here. We talked about it. So the inverse of A multiplied by the vector B. Is this understood, guys? Is this clear? Are we understanding invertibility, matrices that are invertible, and all the characteristics or all the other things that are associated with invertible matrices? Because again, this list we will add more to this list, but this is important to have in your heads. So invertible matrices, the inverse exists. In a homogeneous system, only the trivial solution is the unique solution. The row reduced echelon form of an invertible matrix is always results in the identity. And in a non-homogeneous system, the system has a solution, it has a unique solution, and that unique solution is A inverse times B. So everyone understand that? Can I get some thumbs up, some thumbs down, some shaking my head, anything? So we're good? Okay, so we talk about square, non-square matrices. We talk about non-singular and singular matrices. What other kinds of matrices have we discussed?
Symmetric matrices.
Right, symmetric. And what's a symmetric matrix? I put up a note on.
It's equal to its transpose.
Right. These are the matrices whose transpose is the same. And the transpose is just, in a way, reflecting the entries of a matrix along the main diagonal, right? So we talk about symmetric matrices. So now I want to talk about a few more that we haven't discussed officially yet. I want to talk about diagonal matrices.
Professor?
Yes.
So would skew symmetric just be like a subcategory of symmetric, or is that its own thing?
That's his own thing. So yeah, that's actually, I forgot we talked about that. Because usually we don't give a lot of love to skew symmetric matrices so much. We care more about symmetric matrices because there's more discussed. But yeah, skew symmetric, it's its own thing. It's not a subcategory of symmetric. Skew symmetric is when the transpose is equal to negative A. And as you can tell, negative A does not equal A, so they're not the same. And skew symmetric and symmetric matrices, you're talking about, this only applies to square matrices. So in the realm of matrices, you have square matrices, you have non-square matrices. Of those that are square, you have some that are symmetric, you have some that are skew symmetric, and you have some that are neither, right? Normally, I think we have way more matrices that are neither symmetric or skew symmetric, rather than those being symmetric or skew symmetric. So we have these, right? So far, diagonal matrices are matrices that whose entries that are not on the main diagonal whose entries that are not made are all zeros. And only the entries on the diagonal, on the main diagonal, are non-zero. So what that would look like is a diagonal matrix would have, I'll write D for diagonal. I have D1, D1, D2, D2, all the way to Dn sub n, right? And all of these are zeros. Same thing happens here. So we have matrices that only have non-zero entries along the diagonal, the main diagonal. And we call those diagonal matrices. So these are matrices whose entries on diagonal are non-zero. So how can we describe that? I can describe it as the following. I can say also, in other words, that D sub ij equals 0 if I does not equal j. And D sub ii is not equal to 0. And this is for ij from 1 all the way through n. Okay, so every diagonal matrix, when the indices here are different, the rows and columns are different, right? Then you have zeros, and when they are the same, then you have non-zero. That's a diagonal matrix. And so then my question to you guys is, what do you think the inverse of a diagonal matrix would be? So I'll give you an example. First of all, is this invertible matrix? Yes or no?
Oh,
It's not.
I want to say no because it's
Why?
not a. Yes, it is. It is
Why? Why is it? Why isn't that?
because it's n by n.
3 by 3, it is a square matrix, that's true. But is it invertible?
Yes, because not all the entries are zero. Is that right?
I'm first asking, let me ask, is D invertible? Is D invertible? It should be quite,
It's invertible.
it is invertible. So now my question is, how do you know?
Because not all the entries are zero. Is that right?
That's not a sufficient reason for why a matrix would be invertible. So like, for example, I'll give you a matrix that's not invertible, but that satisfies what you just said. Not all the entries are zero. This is a not invertible matrix, but all the entries are not zero.
Oh, because you can transfer the matrix to the row, a reduced row echelon form.
Right. Yes, because the row reduced echelon form of the diagonal matrix here, it's very simple to make this into ones, aren't they? Like just take half of row 2 and take half of take a third of row 3 and you get 1, 1, 1, right? Along the diagonal. And so you get the identity matrix, the 3 by 3 identity matrix. So do you see how I was able to determine that it was invertible?
So long as none of the rows are fully zeros then.
Right, because that's exactly what happens when you have a non-invertible matrix. If you have a non-invertible matrix and you were to take the row reduced echelon form of this non-invertible matrix, you would get at least one row of zeros in its row reduced echelon form. If it is invertible, then if I were to find a row reduced echelon form of this invertible matrix, I would always result in the identity. And in this case, I get the identity immediately, pretty quickly, don't I? So D is invertible. So we can talk about invertibility. Great. Now, what would be the inverse of this matrix? Now, you would have to say, oh, I'm going to do the whole the whole invertibility, the inversion algorithm, right? But don't worry, it's not going to take that long. Invertible matrices are very nice in this regard. It's not going to take that long. So if I have one, so if I do the division algorithm, right, D to I want to make this go from I to D inverse, right? That's the idea. So I have 1, 0, 0, 0, 2, 0, 0, 0, 3. I got 1, 0, 0, 0, 1, 0, 0, 0, 1. Now, what do I do for the first one? First step, I do 1/2 R2 into R2. What does that become? 1, 0, 0, 0, 1, 0, 0, 0, 3. And this becomes 1, 0, 0, 0, 1/2, 0, 0, 0, 1. And I do it one more time. I do 1/3 R3 into R3. And what do I get? 1, 0, 0, 0, 1, 0, 0, 0, 1. And I get 1, 0, 0, 0, 1/2, 0, 0, 0, 1/3. So my inverse of a diagonal matrix is also diagonal. It's also diagonal. And what's nice about it, it's the same entries as the diagonal, my original diagonal matrix. It's just that the entries on the diagonal of my inverse are the reciprocals. Do you guys see that? So diagonal matrices are very straightforward in this regard. So in general, if D is a diagonal matrix, we have zeros all the way across the matrix except for the diagonals. Then the inverse will be what? 1 over D 1, 1, 1 over D 2, 2, all the way to 1 over D and so on and so forth. Zeros everywhere else. Is that understood? The inverse of diagonal matrices? Straightforward, right? The diagonals are the only ones that are really considered. Everything else are zeros. I is just the row reduced echelon form of D. Right. So the identity, this is invertible because the row reduced echelon form of this matrix is the identity. It's the identity. And I showed you. I went from here to here to here. And this is my row reduced echelon form of D, which happens to be the identity. Good? So we have diagonal matrices which is a subsection of square matrices. And diagonal matrices in this regard are invertible if, so I'll make a note of that. I'll make a note of that. So note, diagonal matrices are invertible if and only if a sub I does not equal 0 for I, 1, all the way through n. So as long as the diagonal matrices have non-zero entries along the main diagonal, it's always going to be invertible. Always will, because I can always find the inverse, which would just be the reciprocal of the diagonal entries. The moment one of these are zeros, any one of these, the moment one of them is 0, it's no longer invertible. And you can see why, because in order for it to be invertible, you would have to divide that 0 entry by 1 by 0. But 1 divided by 0 is undefined. So that's another way to show that. Okay, so diagonal matrices. Okay, and then with the diagonal matrices, for example, also another nice thing about diagonal matrices is the fact that we can take powers of it very quickly. So using that same example, if we have the matrix 1, 0, 0, 0, 2, 3, sorry, 0, 2, 0, 0, 0, 3, what happens when I square the matrix A? And what happens when I cube the matrix A? And what happens when I take A to the kth power? So what happens when I multiply A with itself? A times A. What would happen when I perform matrix multiplication? So pretty quickly, what happens, guys? Do you see how the first row is just going to be 1, 0, 0? And look what happens here. These zeros, right? A lot of these zeros cancel things out. But what happens? We get 0, 2 times 2 is 4, 0. And we get 0, 0, 9. So when you square a diagonal matrix, you're really just squaring the diagonal entries. And then when you cube it, you get the same thing. You get 1, 0, 0, 0, 4, 0, 0, 4, 0, and 0, 0, 9. And you multiply it by 1, 0, 0, 0, 2, 0, 0, 0, 3. And what happens? I get 1, 0, 0, 0, 8, 0, and 0, 0, 27. So when I cube a diagonal matrix, I'm cubing the diagonals. So when I take a diagonal matrix and I raise it to the kth power, what happens to the entries? I raise all the entries in the diagonal to the kth power. So taking the powers of a diagonal matrix is pretty straightforward. You only raise the diagonal entries to that power. Does that make sense? Does everybody see that? So in general,
Yes.
if A is a diagonal matrix, A to the kth power is equal to, well, if the entries in the ith jth column, in the ith row jth column is equal to 0 if they're not on the diagonal and they are equal. So I should write this as to the k, right? And this, if this is to the kth power, then this is going to be equal to aii to the kth power if I does equal to j. So I should write it like this, ij so these are the diagonal entries. And these are the entries off the diagonal. Okay. So far this is what we have: diagonal matrices, powers of diagonal matrices, inverses of diagonal matrices. Pretty straightforward. Any questions about diagonal matrices? No question. So we talked about invertible matrices, not non-invertible. We talked about what else have we talked about? Symmetric matrices. We talked about skew symmetric matrices. And I just want to leave you off with two more things. So that, which one was this? So diagonal matrices. So six. Another kind of matrix that we have are called triangular matrices. And there's two kinds. There's one that's called upper and lower. So upper triangular and lower triangular. And these are the matrices. The upper triangular matrix are the matrices that have non-zero entries above it, but all the entries below the main diagonal are zeros. And then you have lower triangular, which are the matrices, which is just the opposite. We have zeros all above the main diagonal, but you have non-zero matrices, non-zero entries below it. So it looks like you have a triangular region within the matrix above that are non-zero, and then you have a triangular region below that are non-zero. So these are the upper and lower triangular matrices. You see more of this when you talk about the LU factorization. We talk about factorization of matrices. So you can also factor matrices, and that's a whole other realm. But for now, we're not going to be discussing so much factorization of matrices. I just want to touch upon that we have things that are called upper triangular and things that are called lower triangular. So we have triangular matrices, upper and lower. We have diagonal matrices. We have symmetric matrices. We have skew symmetric matrices. We have non-singular matrices. We have singular matrices, invertible and non-invertible. So we've done a lot of matrix, a lot of stuff with matrices. We've done a lot of operations with matrices. We started learning how matrices are involved with systems, right? So we have systems that are non-homogeneous, systems that are homogeneous, and we see how invertible matrices helps in finding the solutions to these systems, right? If we have a inverse of a matrix, then solving a system of equations is almost one click away, as long as you're able to find the inverse on the calculator. Okay, so now I think we are good enough to graduate from all of this algebra, or I would say arithmetic of matrices, and move on to more abstract reality of matrices. So now we're going to be talking about, we're going to have a little introduction to what are called linear transformations. Now, this word sounds like intimidating, probably, transformations, because like, oh, what? Are we going to be transforming? Are we going to be applying transformations like reflections, rotations? And in a way, yes, we are, but it's much more broader than just a reflection or a rotation. It encompasses a lot more. So before we do that, I want to just put some terminology out the way. So we're going to be dealing now with what are called vector spaces. But just remember, just recall the space of R2. Does anybody know what this is? If I write this symbol with R and I put a 2 as a subscript, as a superscript, what does this represent? Let's start with that. Anybody?
Is the symbol alone just real numbers?
It is. This is real numbers. That's right. So if you just had without this, it would be real numbers. So okay, let's start with that then. So this is the set of what? Set of all real numbers, right?
Yeah.
And the set of all real numbers includes what? Natural numbers, integers, rational numbers, and irrational numbers, right? You take all those numbers together and you create the reals. But how is that represented? Do you guys know how that is represented? From a visual perspective?
Oh, it's like a circle within a circle within a circle. Like each.
Yeah,
Each
yeah.
is a
Okay.
subset of each other.
I got it. So you're looking at it from that perspective. I'm saying something else, but yeah, yes. I know what you're saying. Like this, right? Like these are
Yeah.
all the natural numbers. Then you have all the integers here, and then you have all the rationals. Then you have all the reals, right? That's the nestedness, right, of the classification of numbers, right? So
I'm not sure if
yes.
that's what you meant.
No, this is great though. Classification of numbers. I like that. So we do view it this way visually. Yes, so that's right. But there's another way we view real numbers. And when you see this, you're like, oh, that's what you mean. Remember we talked about the intervals, and you want to close an interval, you want to shade an interval, and so you do open circle, close circle. What do you do that on?
Cartesian plane, like in a calculator.
Much simpler than a Cartesian plane. We're not there yet. It's just a number line, right? This is 0, this is -1, this is 1, right? And all of this represents the reals. And then what happens when we take it to the next dimension? What is this going to be now? Do you guys see what's going to be the next dimension? And you said it already.
It would be like adding another number line.
Yeah, exactly. It's adding another quote unquote dimension. So then what do we say? We say that it's an ordered pair, X and Y, such that X and Y are in the reals. I don't know if you guys seen this symbol before. This symbol means belongs to. And this is known as the XY plane, also known as the Cartesian plane. So how do we visualize this? Right? We have a point in space, and that point here is X, and that point here is Y. This is X comma Y, right? But this is how we consider this space R2. We call it R2. And then what happens with R3? Where am I now in R3?
So that would be adding like an so-called extra dimension. So we
An
kind
extra dimension, right? And so then what do we call now? What is that called? The X, Y, Z space, right? X, Y, and Z are all in the set of real numbers. And this is the X, Y, Z space, right? For those of you who took advanced calculus, you have the X coordinate axis, you have the Y axis, you got the Z axis. And then our geometric intuition breaks down once we hit R4. What in the world is R4? You can't say I'm gonna stick another dimension, because it's no longer three, it's still gonna be three-dimensional. So then this idea, now we kind of let go. We kind of let our physical limitation, our understanding of the physical three-dimensional space, we let that go once we go above it. And we just let it be. We let this be a dimension that has four, so we call this X, Y, Z, W, for example. And X, Y, Z, W are all in the reals. And so then when we hit R to the N, our N space, what is our N going to be? It's going to be the set of all. I'm going to call this X sub 1, X sub 2, all the way to X sub N, such that X sub 1, X sub 2, and X sub N, they're all in the reals. We call this an n-dimensional, and without being too crazy with the wording, it's a vector space. We'll talk about vector spaces much more in detail, but just consider this being a space, not physically, of course, but it's just a space that has these elements that each contain n numbers. So it's just an extension of what we already know. We know these, right? We know in this space, we have elements in this space have two dimensions, two numbers associated, X and Y. We know everything that's in this space has three, right? And now we're only extending this to the n-dimensional space. So I'm gonna just put parentheses around the vector. So it's an n-dimensional space. This is three-dimensional space. This is two-dimensional space. This is one-dimensional space. Does that make sense? And so what we call this guy, we call this an n-tuple. So an n-tuple is this x1, x2, xn. That's an n-tuple. You replace the number, the n with 4, for example, a 4-tuple. An example of a 4-tuple would be what? 1, 2, 3, 4. It's a, we're going to be using the word vector now. It's a vector that has 4 entries in it. So an n-tuple is a vector with n entries. Okay, so that's what we'll be dealing with. That's what we're going to be dealing with. Okay, and then these vectors can be expressed in 2 ways. So a vector, we're going to define it as is a matrix that is either n by n or 1 by n. So a vector is a matrix that either has n rows and one column, or one row and n columns. And we're going to just call that from now on a vector. That's what the vector is. So when we have a n by 1 matrix versus a 1 by n matrix, again, these are both vectors. If it's n by 1, then this is called a column vector. If it's a 1 by n, this is called a row vector. So if I have a column vector, I can write it this way. Yeah, A1, A2, all the way to AN. That would be my column vector. And if it's a row vector, I'm going to have R1, R2, right? All the way to Rn. So you can express vectors as row vectors. If it has this dimension 1 by n, you can express vectors as a column vector. And this is more commonly used. More commonly used. And we've been using a lot more column vectors when we talk about matrix equations, right? When we do AX equal to B, both of these are column vectors. They've been column vectors the whole time. And associated with the row vector is something called the comma delimited form. Which just means that if I have a vector, I can sometimes write it like this: B1, comma, B2, comma, B3, Bn. So all I'm saying is that I can write, so an n tuple is a vector. N tuples are considered to be vectors. So we can take an n tuple such as this 1, 2, 3 and either make it into a row vector or a column vector. So the row vector for this one, so if I call this V, right? Then the row vector would just be 1, 2, 3, 4. And the column vector version of this would be 1, 2, 3, 4. That's all. So comma delimited form just means I have commas in there. The row vector just means that my numbers are across a row with no commas. And the column vector are numbers within a column. Does that make sense? So we have column vectors, row vectors, and they're just direct expressions of n tuples. So now we'll be dealing with things that are living in n-dimensional space, whether it be 3-dimensional, 5-dimensional, 10-dimensional, and so on. Okay. So the next thing we have to talk about are called the standard basis vectors of Rn. Pretty heavy here, because there's tons to say about what it means to be a standard basis vector. There's tons. But for now, there's tons to say about a basis vector. But for now, standard basis vector seems like it's very formidable, but it's really not. So what's a standard basis, or what's a vector that's considered as a standard basis of Rn? It's these vectors. So E1, I'm writing it as a column vector. E2, E3, We usually use the word E for standard basis, the letter E. And so on and so forth, right? And E sub n. This is the set of standard basis. It's simply a column vector that has all zeros along the entries except for the index given by the subscript. So if I'm E1, then the first entry has to be a 1. If I'm E2, then the second entry must be a 1. Everything else must be 0. E3, the third entry has to be a 1. Everything else has to be 0. And of course, the nth entry. And so in general, E sub I is where you have zeros all across everywhere except for the ith entry. That's all a standard basis vector you should know, should think about. That's all it is. So in R2, what's going to be the standard basis in R2? So example. We have E1, right? Which is what? 1, 0. And we have E2, which is what? 0, 1. And that's it. Now, visually, what is that going to look like? And vectors, we usually write them as arrows. Draw them as arrows. This is 1, this is 1. So this one here, this would be E1. And this here would be E2. Sam, you raised your hand.
Yeah, I just noticed in the general rule you made above, it says ith entry must be a 0. Should it be a non-zero, you mean?
Pardon me. I meant to say it's a 1. Not just that that's my mistake. I just see all zeros and I put 0. Very good. Thank you, Sam. Yeah, it should be a 1. Must be a 1. Not just non-zero. It must be a 1. That's only for standard. So standard has 1s in the entry associated with the subscript of the vector. So if it's the ith entry, if it's the ith standard basis vector, then you have a 1 in the ith position. That's what I meant. Thank you. Thank you for that. And so in R2, what are the standard basis vectors? It's going to be 1, 0, which is associated with the point, right? It's associated with the point 1, 0, and then you have this point here, 0, 1. And then just to give you a standard visualization, standard basis vectors in R3. So we got 1 here, right? This is 1, 1, 1. This would be E1. This would be E2, and this would be E3. And E1 is what? What is E1? 1, 0, 0. E2 is what? 0, 1, 0. And E3 is what? 0, 0, 1. So that would be the standard basis vector, set of standard basis vectors in R3. In R4, you can't visualize it, but it'll be the same thing. It'll be 1, 0, 0, 0 for E1. E2 would be 0, 1, 0, 0, and E3 would be 0, 0, 0, 1, 0, and then E4 would be 0, 0, 0, 0, 1. So that's the idea. Does that make sense, everybody? Standard basis. It should be clear with that, right? So that's standard basis vector. So then, okay, now we have that. Now, how is this at all related to what we've been doing so far with matrices? Well, the thing is, every vector or n tuple in Rn can be expressed as a linear combination, and this is when things get interesting, a linear combination of the standard basis vectors. And you'll see eventually why this is even, why you even care about this. So for example, if I have a n tuple, right? x1, x2, x3, xn. So x is in Rn. So suppose x is living in Rn. Then we have x is an n tuple. And we can express this vector, whatever that vector is, as a linear combination of the standard basis vectors. And we talked about linear combination in the beginning of the semester, probably lecture 2 or 3. But we kind of just got off that. We're definitely going to be on that now, heavily. And what that means is, does anybody have an idea of how to represent x as a combination of E1, E2, all the way to En? Does everybody see that or no? So if I write this as a column vector, x1, x2, xn, right? You know how else I can associate this? I can also write it like this. x1, 0, 0, plus 0, x2, 0, dot, 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 0, 0, 0, xn, right? Can't I do this? Because when I add these up, when I add these together, I get this. So I can disassociate them this way, right? But then can't I do this as well by the property of scalar multiplication with matrices? Because remember, vectors are matrices. I can write this as this, right? x1, 1, 0, 0, plus x2, 0, 1, 0, right? Plus x sub n, 0, 0, 0, 1. Can't I do this? But then what are these? What are each of these vectors now? They're the standard basis vectors. And this sum, the way I just wrote this out, is what's called a linear combination. It's like saying I have a sum of the scalar multiples of E1, E2, and E3. That's what a linear combination is. It's a sum of scalar multiples of vectors. So then I could have written as x, the arbitrary vector that I'm given. I can write it as x1, E1 plus x2, E2 all the way to xn, En. Do you guys see that? And I can continue this kind of writing and write it as a summation of x sub I, E sub I to the n. This here is very important. And this is true for any, right? This is true for any vector that I'm given in any n-dimensional space. I can always write it as a linear combination of the vectors, the standard basis vectors. So this here means that x is expressed as a linear combination of the standard basis vectors E1, E2, En. Does everybody see that? So any vector in n-dimensional space can be written as a linear combination of the standard basis vector. And it's kind of almost now, hopefully, it's a bit straightforward. So example, what if I have the vector 1, 2, -3, -7? Express this as a linear combination of the standard basis vectors. So how would I write that? Express X as a linear combination So then how would I write that? As a linear combination of the standard basis vectors. How
Would
many?
it be,
Go ahead.
I was gonna say, would it be like we did it before? So it would be like E sub 1, 1, 0, 0, 0, plus, and so on.
Yeah. But now, yeah, that's right. So this would be what? This would be 1 times 1, 0, 0, 0 plus 2 times 0, 1, 0, 0, right?
Yeah.
Minus 3 times 0, 0, 1, 0. Minus 7 times 0, 0, 0, 7. I mean 1, pardon me. And which I can rewrite this as 1 times E1. I already know what E1 is in the 4-dimensional space, right? Plus 2 times E2 minus 3 times E3 minus 7 times E4. That is X. And that is a linear combination. Do you guys see that?
Yeah, that's clear.
And you can do that for any. Yes?
I just have a question. What
Yeah.
do we call E again?
Oh, so we named E. So in the beginning, right? We named E. E sub I, this is really it. E sub I is the ith standard basis vector that has 1 in the ith entry and zeros everywhere else.
Okay.
So maybe I should write that as well. And zeros everywhere else. You can think of the standard basis vectors as like the most simplest. They're like the building blocks of your n-dimensional space. So in R2, what are the building blocks for every other vector? It's the vector 1, 0, and 0, 1. Give me any vector. I don't care what vector it is. Wherever it is in space, I can always write it as a linear combination of these two vectors. Give me any vector in 3-dimensional space. The building blocks of it are these small vectors that all are length 1. 1, 0, 0, 0, 1, 0, and 0, 0, 1. Give me any vector. I can rewrite that vector as a linear combination of these vectors. And this goes on and on and on. So this is important that I can rewrite any vector as a linear combination of these very elementary, basic, standard, what are called standard basis vectors. Okay, is that clear?
Yeah, it's clear.
So these vectors, you can think of it as like the most, what is that called? Like, it's the fundamental unit of of a vector space in this regard. They're like the atoms of their vector space. You can't break it down any further. You can, but that's what we start with. We start with these vectors. Okay. Now, so guys, do you guys know what a function is? I know this is a, you guys should know what a function is. So what is a function?
It's an expression relating one or two more variables.
Yeah, it is an expression. It can be expressed as an expression, but doesn't necessarily have to be an expression. It does relate to things though, right? Anybody else out there what a function is? Nobody?
A relationship.
It is a relation. What kind of relationship? Yes, Alexa, it has to do with inputs and outputs. Now we're talking. Now we're getting somewhere. Yes, there's inputs and outputs. There's a relationship, but there's also a specific kind of relationship, right? So we're going to a very fundamental idea in mathematics. And I know for most of you who are computer science majors and all the coding that you have to do, you write functions all the time as well, right? So you have an input and an output. But in mathematics, there's a very specific relationship between the input and output. Every input can only have what? Right, Sam. So every input has only one output. So it is a rule. So a function is a rule that assigns an input. I should say every input value to one and only one output value. And now we can say it has a unique output value. You see this idea of unique. Yes, Baldwin.
I was just going to say, so basically every input in the domain has exactly one element in the range.
So now we're going to use another. Yes. Now we're extending this idea, right? We have domain and we have range. And the domain is the what? The set of all input values. And the range is the set of all output values. And then F, what is F? F is the rule. F is like the assignment. F is the relationship that exists between everything in the domain and everything in the range. That's what it is. Now, we're going to be using a few more like fancy things, fancy terminology. Now, the range is the set of all output values. But we're going to be talking about something bigger than the range. The range exists in a space. Let me just make this a little bit bigger. Called the codomain. So codomain is the bigger space that the range is a subset of. Okay, and that's going to be important when we talk about what are called transformations. So the codomain is the larger, is the set or the space where the range lies in. Okay, so the range is inside the codomain, but the codomain does not include, it includes the range, but plus it includes more things. And there's another terminology that we use for the range. So the range is also used, is also called the image under F. So it's the image. So these words, they start to become kind of jumbled, right? This is what you learn with functions: input, output. X goes to Y, domain, range. Now this word function is being literally transformed to something that's called the transformation. And it takes things in the domain and puts it in what's called the codomain. And in particular, that word range, now we're going to use the word image. And the values associated with the domain, which are the set of input values, we're going to call this the pre-image. So this is just, this is like what we deal with when we talk about invertible matrices, non-invertible matrices. We can also call them non-singular and singular. Same thing here. Domain, range. Now we have a new way of calling it: pre-image of a function and the image of a function. It's just another word. It's just another term. But you guys already know this. It's just that it's a new term that you guys are dealing with. Okay? So we're good with this. So image of a function is the range of the function. The pre-image of a function, it's the domain. And the range sits inside something that's called the codomain. So everyone clear with that? Yes. Okay. Okay. So here we go. So there's a whole setup, a whole buildup to talk about this. So I'm going to do a definition. So we call a function t. So again, this is a function with domain in Rn and codomain Rm. So n and m are not necessarily the same. They could be, but not necessarily. So we're in an n-dimensional space for our domain, and our codomain is an m-dimensional element. So when we talk about functions, right, what do we normally, where are we normally in? We're normally in the reals, and then our output is in the reals. We're in this space. We're in R1. We've been in R1 the whole time. And that's why we have this like dimensional. We have R1 is our inputs, and then R2 is our outputs, right? And then for those of you who took calculus 3, multivariable, right? We have the 3-dimensional space. And how that sometimes we had our inputs were 2-dimensional, right? And then our outputs were 3-dimensional. And sometimes vice versa. So now we're going to be dealing with the idea that we have a transformation that takes something in the n-dimensional space, and then when you assign it to something in the m-dimensional space, still a function though. That's one thing. So we call a function t with domain Rn and codomain Rm, we call that a transformation. We call a function that takes something in n-dimensional space to something in m-dimensional space, we call that a transformation. And we call it transformation from Rn to Rm, or we call it a mapping. So again, there's going to be a lot of jargon here. Hopefully you see that they're the same thing. From Rn to Rm. And we denote by the following. We denote it by the following. So this is how we denote it. We say T colon Rn arrow Rm. That's how we express a transformation. We're saying that this, so this is the name. You can call this like the name of transformation. Mapping. This is my domain. And this is my codomain. So these letters are going to change. This could be an F, this could be a T, this could be just a different kind of letter. The first thing that you see here before the arrow indicates the domain, where your domain lies in. And the codomain is where your image lies in, where your range lies in. And this arrow just indicates that I'm going from here to here. So that's why we use this arrow, because this arrow kind of gives you a sense that you're mapping something, right? You're assigning something in here to something in here. That's all it is. So a function has been a transformation this whole time. Yes, yes. So this whole time, okay, this whole time, up until Calc 3, up until multivariable, right? Our functions have been this form. Our functions have been functions whose input or domain is in the real one-dimensional space, and you map it to something in the real, in the one-dimensional space. That's what we've been doing. So the moment you do this, like y equals f of x is what? One-dimensional. Y is what? One-dimensional. So you've been dealing only with these functions exclusively for like the longest time, since Algebra 1, since you talked about linear functions, all the way until Calc 2. You've been dealing with these functions only. But then there's a plethora of other functions that exist. So it's a general term, we use the word mapping or transformation. Crazy, right? So like I said, this is where linear algebra comes into play, where it kind of demarcates the difference between elementary, fundamental mathematics and the more advanced thing. This is when you talk about any kind of no, you haven't been lied to. You just haven't been told the whole truth. That's all. And this is just the beginning. We're just getting our feet wet. Let me tell you, this is nothing crazy yet. Nothing crazy yet. Okay, so that's that, right? That's that. Okay. So now, how is this related? How is this connected to matrices? That's really the question. So how is this related to matrices? So let me tell you another definition. A matrix transformation is a transformation, right? It's a transformation that assigns an element in Rn to an element or vector, you can say, in Rm by left multiplying. So I'm gonna use what do they use? They use X and W. So I'm gonna use an X arrow here to indicate, so let me just write this, an element in Rn. So this vector X is an element in Rn, and I'm gonna call an element of Rm. I'm gonna call this Y. By left multiplying X with a matrix A to get y. What that means is that T, so the matrix, so the notation for this, the notation for matrix transformation is that T now, I have a matrix associated with T. So you see how here, this is more in its general form, what a transformation is. So this is a function. This could be functions that have two inputs and then one output, or two outputs, two input, three outputs, two inputs, or whatever combination you have, right? But now the moment you put an A here or like a B here or whatever, that A is my matrix. So this is like, A is like a matrix. And I'm still taking things in Rn and mapping it to something in Rm. And in particular, I can write it this way. I can say that Y is X, when you take X as the input, right? This is my input. So this idea of function still exists. I have an input and an output, domain range. But now what am I doing to the input? My input now is a vector. My output is another vector in a different dimension. They're in different dimensions. And I'm transforming that vector in the domain by left multiplying it by a vector, a matrix A. So this here is the same thing as saying Y is equal to A multiplied by X. So this whole time up to this point, when we talk about multiplying a matrix A with X and I get a new vector, we've been applying transformations, matrix transformations the whole time. It's like you learn how to, you learn how to crawl, you learn how your ABCs before you can actually write an essay and all that. So you learn the basics, the mechanics of matrices, and now we're looking at the more theoretical underpinnings of linear algebra. So we really care about spaces. We really care about different dimensions, going from one dimension to another, and how to map things in one dimension to another. Okay, and you can write this also, or you can write this as X. When you apply the transformation A, you get Y. So this is just notation. Oh, I should write it up here. Does that make sense?
Yes.
So we talked about transformations, what they are. Now we're refining that definition to matrix transformations. And now I'm going to do one more thing. And these are called an operator. An operator. An operator is a matrix transformation. So an operator is a matrix transformation where, so I'm gonna call it T, where T goes from Rn to Rm and N equals M. So transformations or matrix transformations that map something in Rn to another thing in Rn, or I should say, in other words, T goes from Rn to Rn. So for all matrix transformations that are under this special case where N equals M, It's called an operator. It's still called a matrix transformation, but it's a specific kind. It's called an operator. So we also talk about operators specifically. Okay. Boy, oh boy, right? Crazy, right? Crazy stuff. So then we have examples. I'm gonna give you just simple examples of transformations, matrix transformations. And they're kind of like the usual suspects. There are ones that make everything zero, and there's ones that do nothing. So what are those called? So we have things that are called the zero transformation. So that's when you take something like this, t of x, right? So this is the transformation that has the zero matrix associated with it. So if you take zero, the matrix zero. So when I say zero, I'm talking about the matrix or the zero matrix. And I multiply it by any vector. What am I going to get when I multiply a vector with a matrix that had all zeros? It's zero. That's right. It's a zero matrix. That's not that special, right? And you also have something that called the identity. The identity. And in order to talk about identities, we call them operators. Because the only matrices that are identities are square. So if there's square matrices, then the dimensions have to match up. And so we have something like this, Ti. This is I times X, which is X. So these are the usual suspects. These are things that either make everything go to zero or doesn't do anything, just leaves things be. Okay. Okay. And if we study this a bit more, this idea that if I take a matrix transformation and go from Rn to Rm, then does anybody know what the dimensions of M have to be? Of A, I mean? What are the dimensions of A? Now, how would you know that? Yeah, Sam?
Would it be n by m?
M by N, right. How do you know?
Oh, I guessed. I'm sorry.
Oh, you guessed.
Yeah, I didn't have. Yeah, I just figured.
Fine. That's fine. So remember what we did? We took something in X, we took something in Rn called X, and we took something in Rm called Y, right? And then we have a matrix A that supposedly when I take A and I multiply it by X, I get Y, right? That's the whole idea behind this, right? That's what this means, correct? And X is what? X is a column vector in n-dimensional space. So what that means is I have something like this, x1, xn. I have a matrix A, and the result is something in m-dimensional space. So remember matrix multiplication? This has dimensions what? N by 1, right? This has dimensions what? M by 1, right? So what does this have to be then? Remember, in order to multiply, the inner dimensions must be the same. So this must be n. But then the result is the dimensions of the product has to be m by 1. So this must be M. So a matrix A that takes something from Rn to Rm must have, in other words, A must have M rows and N columns. That's how they're connected. So this is going to be like A11, A12, all the way to A1N. This would be A21, A22, all the way to A2N, all the way down to AM1, AM2, all the way to AMN. That's going to be the dimensions of A. That's how it's related. Does that make sense? Okay, and then a few more things and we'll be done for today. There's some properties, I would say important properties. Important properties of matrix transformations. And it's only two main ones. And we can talk about the other ones that exist later. If you take a matrix transformation, so let TA be a matrix transformation that goes from Rn to Rm. Then what happens is you can take the matrix transformation of one of the vectors and add it to the matrix transformation of the other one. And U and V are in Rn. Right? And there's another characteristic is that if you take a scalar multiple of a vector, and so K is a scalar number, then this is equal to K multiplied by T, the transformation of just U, and you just multiply by K. Now you should be able to say that this is true because of the idea of matrices. Because this is associated with A, then what you can do is, so just consider 1 for now, okay, for I. So TA U plus V, this means that there is a matrix A that when you multiply it by U plus V, I get a result back, right? But because of the distributive property that matrices obey, I can do this. And then this itself is TA of U plus TA of V. And the same thing goes for this statement here. So these are very important properties. These are called linear conditions. So what we're saying is that matrix transformations are what are called linear. And sometimes we just start using the word linear transformations to denote matrix transformations. And let me do one quick example and then I'll be out of your hair. So an example of this, right? So if I want to find, right? I want to find what's called the standard matrix of a linear transformation. And T goes from R2 to R3. And I give you that T takes the vector x1, x2. Remember, this is the input. And the result is something like this: 2x1 plus x2, x1 minus 3x2, and negative x1 plus x2. And what I want to find is, what is A? I should call this A, right? What is A? It's a pretty straightforward way of doing this. Plug in E1 and E2. So if I plug in E1 to this, remember that equals what? 1, 0, right? If I plug that in, what happens? I get 2 times 1 plus 0, 1 minus 3 times 0, negative 1 plus 0, which is what? 2, 1, negative 1. It's this matrix right here. It's this column of vector. And if I plug in the other one, the other standard basis vector, I get 2 times 0 plus 1, 0 minus 3 times 1, negative 0 plus 1. What I get is 1, negative 3, 1. And what that tells me is that these are the columns of A. A is 2, 1, negative 1, 1, negative 3, 1. Now you may be like, how come? How is that the case? Well, if you do A times E1, what do I get? I get 2, 1, negative 1. You can try it yourself. You can check. When you multiply by E1 to any matrix, you get the first column. When you multiply by E2 to any matrix, you get the second column. And if you have more dimensions, if you have E3, E4, En, right? The E, when you multiply, so in general, A multiplied by EJ is equal to the jth column of A. And that's why we talked about standard basis vectors, and that's why we talked about vectors and so on and so forth. So sorry for taking 3 minutes after. So I'll stop here.